Good morning, students. As you know, my name is Sudha Pandey, and we are going through a chapter. Chapter name is surface tension. Okay, so in this chapter, we will discuss about the rise of liquid in a capillary tube. Means, firstly, we have to know that what is capillary tube. Then we are in need of to know that how there is a possibility arises due to which the liquid rises up or it can depress in the capillary tube. Means it is not necessary that the liquid always rises, but it can also depress. Okay, so what are those conditions, how this happens, these all things we will discuss in this lecture. Okay, so let's get started. As you can see here that it is clearly mentioned when one end of a tube of a small radius is basically called as bore, B-O-R-E, bore. So if the bore is very fine, very thin, we can simply say a small bore is there, then that tube is known as your capillary tube basically. Okay, so if I draw a diagram for you, then you can simply say that it will be like this way. Okay, so this is your uh, capillary tube having a very fine bore like this way. Okay, so this is the, you can simply say, the radius of the bore, this one here. This is your fine bore, a very small radius is there. Okay, this tube is basically your capillary tube, and we call in short that is CT. So CT is basically refers to capillary tube. So a tube which have a very fine bore, very small radius, has an ability so that when this is dipped in a container, suppose this is your container having some liquid in it like water, so it is your water, and you can simply see that the water automatically starts rising up in the capillary tube up to a certain height. Or if we filled that container with mercury itself, suppose this is your mercury like this way, and you put the same capillary tube in the mercury container, then what will you get? Then we can simply see that this is your capillary tube like this way. Okay, uh, this is the second surface of the capillary tube, and this is the fine bore as I have already explained to you. This is the fine bore. Now you will see that the, the mercury will move in the downward direction like this way. Okay, it means we can simply say that in case of water, the water rises up in the capillary tube, whereas in case of mercury it goes in downward direction, or we can simply say that it depressed inside the capillary. So why this happens? This happens due to the contact angle. As in the earlier lecture I have discussed about the contact angle. What is the contact angle? So if the contact angle is less than 90 degree, as in case of water, you have seen earlier, the liquid rises. Okay, But if the contact angle is greater than 90 degree, it is depressed. So this is the case of your water, and this is the case of the mercury. So I hope that this thing is now clear, that there is a capillary tube, and capillary tube has a property depending upon the contact angle of any particular fluid, that if the contact angle is less than 90 degree, then the fluid will rise up. If the contact angle is greater than 90 degree, then it will depress. Okay. So we will discuss this thing, why and how much height a liquid can attain, or how much height it can be depressed inside the capillary tube. For that, we have to draw a new diagram for you. So this is your diagram. As you can see here, this is your capillary tube in two different positions. We can simply see. This is the moderate condition, and this is the significant position. So here you can simply see that this is your water, like this way. The water is up to height h when the capillary tube is placed in the container having water. Okay, this is height h. Up to height h, it is rising, because here we have taken the water. Okay, and the contact angle for water is less than 90 degree, you know. Okay, now after getting a certain height, it is quite easy to understand that if the water attains a certain height h, and after that further rising of the water stops, it means finally the water or that particular liquid have in equilibrium position. So if we have to find the height of rise in capillary tube, rise or depress, whatever, clear, in capillary tube, then there are two basic concepts. First concept is based on condition of equilibrium. First concept is condition of equilibrium, like this. Okay, and second, as you know that excess pressure in a liquid drop. So there are two methods. We can simply say that by using any one out of the two, you can easily calculate the height of rise or depressed in CT. Okay, so firstly we will discuss the first condition, first method. So first method or first condition, that is the condition of equilibrium. For that you have to know that if any object, whether it is fluid, then if it is in equilibrium, then all the forces must be balanced. Okay, so we will discuss how many forces are there inside the capillary tube. So firstly we will draw the diagram. So as you can see that this is your one phase of the capillary tube, and then we have another phase of capillary tube. You can draw like this way, this one. Okay, this is the second phase of the capillary tube, and the tube is in a container. So this is your container, like this way, and it has water, let's suppose, clear. So where is water? Water is like this way. This is your water layer. the capillary tube has fine bore, as I have already told you, then the water rises like this way up to a certain height, and the height is basically h. Now you can simply say that the upper surface has a meniscus shape. Okay, so the shape of the upper layer will be like this way. You can simply say, so that we have a angle of contact. So angle of contact can be, we can say that we can draw like this way. When we draw a tangent over it, this is your tangent on the water surface at the point of contact and inside the liquid. So this is your angle theta, or we can simply say angle of contact. Okay, now we have to discuss about the condition of equilibrium. So condition of equilibrium says all the forces must be balanced. All the forces must be balanced. So there is a requirement. We can see that what type of forces are there. So as we have some different points, as you can see here, that let's suppose we have different points. Let's suppose this is your point A, and this is point of contact, that is point B, and here a point C, this is point D, and this is your point E. One thing is very clear, that point C, the point D and point E are at same level, are at same level. So because all the points are at same level, it means must have equal pressure, and due to this pressure a force will be there, and we know that the basic formula, pressure is nothing but force upon area. So it gives force which is due to the pressure, so pressure into area. So we can simply say that because the point C, D and E are at the same level, so pressure whatever is at point C, that must be the pressure at point D, and that must be equal to the pressure at point E. Okay. Now if we talk about the pressure at point A, pressure at point A. So pressure at point A, if it is the atmospheric pressure, so PA, let it be P. P here, P is the atmospheric pressure. Okay. And point C is also feels the atmospheric pressure, so it will be also equal to PC, and it will be also equal to PD. So we have final result that the pressure at point A, that will be equal to pressure at point D, and both pressure will be equal to P, that means atmospheric pressure. So we have a result by using the formula F equal P into A, that the force at point A must be equal to force at point D, and that will be P into A. And what is A? A is the area of the capillary tube, so it will be pi r square. Okay, so these two forces are there, and the pressure will be inward, or we can simply say that if we talk about the point A, then firstly we have to draw the diagram again. This is a little bit typical process, I can simply say. So once again I have to draw the diagram. So this is your capillary tube in a zoomed view is there. So this is the container. We can simply say like this way, and we have a liquid. You can see that liquid is water like this way, and we have 2 points here. Basically, one point is your point A here. This is your meniscus here, point A. So it has a force which is inward direction, and here is your point D, so which also has a force that will be in upward direction. And I have already told you that the force at point A is equal to force at point D, so these forces will be cancelled out. Okay, it means these two forces are not actively plays a role for rising the liquid in the capillary tube. So where are the other forces which are responsible for the rise? So as we can simply say that some liquid is there in the capillary tube, so it must have weight. So let's suppose the weight is W. Okay, and we have a surface tension. As you can say, this is angle theta. So by using Newton's third law, because whatever force is applied on the surface of the liquid, so the same force will be applied to the opposite side or at the same angle theta. So we know that the formula of the surface tension in terms of force, that is force per unit length. And if we take the small portion of this meniscus or this layer, then we can simply write S equal F upon dl. Okay, so we have force on the small element of the meniscus, that will be S into dl. So if we want to calculate the force here, we can simply write that this will be S times dl, and this is the small portion of the meniscus dl. Okay. Now because this is at angle theta, so it have two components like this way. So we have to draw another diagram for you. As you can see that this is your SDL and this is your angle theta. Here you can see in this diagram. So it has two components because it is a force. So force is a vector quantity. So it has two components. One will be SDL cos theta and the other one is SDL sin theta. Now as you can simply see that in the meniscus, if we draw the meniscus like this way, we can simply draw, then you can see that if the element are here, then here, then here, then here, and here, and here, means anywhere you can choose the elements. So each element have two components. One will be dl sin theta, whereas the other will be dl cos theta. Okay. Now the elements which are on the right side or the left side, that will be S dl sin theta, and here also S dl sin theta, because according to the condition of symmetry. So these two will be cancelled out each other, but all the forces which are in the vertical direction, they will be added. So it will be S dl sin theta, cos theta. So basically we have to calculate, suppose this is small df due to the small element dl, so this will be df. Okay, so if we have to calculate the force, then force will be nothing but the integration of the all the forces, that will be S dl cos theta. Okay, so it can be written as S times cos theta and integration, that will be dl. And what is the DL? DL is the periphery, or we can say the circumference of the meniscus, or we can say the circumference of the layer. So we have force that is S into cos theta into 2 pi r. Here r is the radius of the bore, or we can say radius of the capillary tube. So r is the radius of capillary tube. Okay, so this force is basically in the upward direction, as you can see in the diagram. This is the direction of the SDL cos theta, or we can say the net force will be in the upward direction. And one more force is there, that is your capital W, or we can say weight of the liquid inside the capillary tube. So that force must be balanced. So what we should write? We should write the force which is in the upward direction, that must be equal to the weight which is in the downward direction. And the force which is in upward direction, that is your, you can simply say that F cos theta into 2 pi r. So it will be S cos theta into 2 pi r. Now weight. So weight is nothing but, you can simply write that mg. M is nothing but volume into density into g. So this will be S cos theta into 2 pi r. So it can rewritten as 2 pi r, and that is equal, and now volume. Volume is area into height. So area is pi r square. The area of the capillary tube, or we can say the bore of the capillary tube, into height h, because up to height h the liquid is rises into rho into g. So when we solve it, then what we get like this way. So you can see that r and r cancel out, pi and pi cancel out. So we have h, and that will be equal to 2s cos theta and divided by r rho g. So this will be the height, or we can say the depression of the liquid in the capillary tube. So this is your first method, which is based on the condition of equilibrium. All the forces we have to balance, and then we get the final result. I hope and I believe that this is clear. Now what is the second method? Second method to solve the same derivation is based on excess pressure of the liquid drop. For that we have to again draw the diagram like this way. You can simply see here. This is your capillary tube like this way, and this is your container like this way. This is your container, and it has liquid. So let it be liquid, or we can simply say it is water. So if it is water, then it will be rises up like this way. Okay. So, and the upper side, it has a surface, or we can say the meniscus, which is in the shape of a bubble, we can assume. We have a point A, as I have already told you that there is a point A. There is a point, we can simply say that point B, there is point C, and here is your point D. Okay, this is the height h. Now we know that the formula for excess pressure. So excess pressure, that is delta P, and given by 2s upon capital R. What is capital R? Capital R is radius of bubble drop, or we can simply write drop. So radius of drop, that is your capital R. So Here this is small r, so small r is the radius of the capillary tube, but this is your capital R, which is the radius of the drop. This is excess pressure, we can represent as delta P. Now we can see that if this is the surface, or we can say the concave side of the meniscus, so this is point A, and below it there is a point B. Sorry, if this is B, C, D, then it may be E point, and this is your point C, which is H height below the point E. The A point is at concave side, so it have more pressure with compared to E side. So we can simply write that the pressure at point A minus pressure at point E. Okay, this is the excess pressure. That must be equal to 2S upon capital R. I hope that this thing is clear to all of you. Now one more thing, but that if we have to calculate the pressure at point C, so pressure at point C, that will be nothing but pressure at point E plus H rho G, because we know that as the depth increases, the pressure also increases. So from the point E, the point C is H height below. So the pressure at point C, that will be equal to pressure at point E plus H rho G. Now what? We have already discussed that the pressure at point C, that must be equal to pressure at point B, and that must be equal to pressure at point E. Okay, so it means we can simply write the pressure at point C, that is equal to the pressure at point A. So in place of PC, we can write PA. So PA, that will be equal to PE plus H rho G. Okay, now what? As you can see that we have a result P equal P plus H rho G, and we also have a result that PA minus PE, that is 2S upon R. So by using these two expressions, we can write what? Firstly, we will write that PA minus PE, that is your 2S upon capital R, and the second expression P equal PE, so PA equal PE plus H rho G. So place the value of PA here, so we have PE plus H rho G minus PE, and that is 2S upon capital. So PE and P cancel out, and we have H rho G, that is equal to S upon capital R, or simply H equal 2S upon rho G capital R. So this is the formula which is in terms of capital R. Capital R is the radius of the, we can simply say, the bubble or the meniscus or the upper layer. So we have to convert this capital R into small r. For that we have to see the diagram. So as you have diagram like this way, this is your capillary tube, like this way. This is the very zoomed image of that diagram, and the upper side has this side this way. Okay, and this is, so this is your small r, means the radius of the capillary tube. Okay, and we can simply write that if this is your small r and this is your capital R, okay, this is your capital R, okay, and this is your angle of context theta, and this is your angle of 90 degree. So if we take cos theta, so it will be small r upon capital R, or the capital R can be written as small r upon cos theta. Okay, so whatever we have the result is small h equal to s upon rho r, rho g r. So small h equal 2s upon rho g capital R. So place the value of capital R here, and we have 2s cos theta upon rho g small r. So this is your final result, which is in terms of the radius of the cavity. So these two methods are possible to derive the rise of the liquid in any city. I hope and I believe that these two methods are quite easy to understand. And if you feel any difficulty, then you can try by yourself once. Okay, so I hope and I believe that this topic is now clear for all of you. This is your example 14.8 from the book written by Padmasri S. Verma sir, and the book name is Concept of Physics. So in this question, what we have given that we have a capillary tube, and the radius of that tube is 0.20 millimeter. And as I have explained to you, as I have told you, that the radius of the city is represented by small r, so it will be 0.20 mm, or it can be rewritten as 0.20 into 10 to the power minus 3 meter. Okay, find the height means we have to calculate the value of h here, so it will be question mark. And surface tension capital S, that is given to 0.075 Newton meter inverse, and the density is also rho given to you, that is 1000 kg meter inverse cube, and G we have to take that 10 meter second inverse cube. So firstly we have to write the formula, and the formula you know that the formula is H, that is your 2s cos theta upon r rho g. Okay, so put all the values 2 into s, and s is your 0.075, so 0.075 into cos, and theta for the water, that is 0 degree, divided by r. So r is also given to you, that is your 0.20 into 10 power minus 3, so 0.20 into 10 power minus 3. Density, that is 1000 for water, you know, and this one is 10. So it can be rewritten as 2 into 0.075 into, and cos 0, that is 1, divided by 0.20 into 10 to the power minus 3 into 10 to the power 4, because this is 10 to the power 3 and 1, so 10 to the power 4. Now what? If we remove this decimal, then 10 to the power 3 will be lower side, and if we remove this decimal, then 10 to the power 2 will be upper side. Okay, so we can finally write like this way: 2 into 75 into 10 to the power 2, and divided by 20 into 10 to the power. So it is 4 plus 3, 7, and minus 3. So it will be 4. So 10 to the power 4, because 10 to the power minus 3 and that is 10 to the power plus 3. So cancel out, only 10 to the power 4 remains. So but we should write now, we should write like this way, that is 2 into h, 2 into 75 into 10 to the power 2, so 10 to the power 2, and divided by 20 into this is 10 power 4, so 10 to power 4. So 2 will be cancelled, that will be 10, so 75 into 10 to power 2, and that is divided by so it will be 10 power 5. Okay, so it can be written as 75 into 10 to power minus 3, or it can be written as 7.5 into 10 to the power minus 2 meter, or 7.5 centimeter. So this is your final answer. I hope and I believe that this question is clear to all of you. So as I have explained to you the complete derivation and the numerical based on that derivation. So if you try by yourself, then you can do also very easily in the same pattern as I have followed here. Okay, so just try to solve each and every numerical by yourself, and keep in touch with me, and just float in the world of physics along with me. Thanks for watching me, thanks for listening me, and best of luck.